Hello, everybody, and welcome back to SciByte, where we explore the mysteries of the universe and all the tools and technology that science is using to get to the bottom of it all. I, as always, until you get sick of me, am your host, Jeremy, and joining me on the Skype line, as every week, is the smart half of this dynamic duo, Heather.
Hi, guys. This week, we're going to be talking about the sun, solar weather, what we look at it, why it's important.
All sorts of different stuff. And I will tell you, there are two reasons that this is actually a hot topic to... Okay, I didn't intend for that to be this week's pun. I really didn't. I really just wanted to say that this was going to be a hot topic to cover. So, but let me talk about those two reasons. The first is that it's only been within the past decade, maybe 2 decades, that science has really started to hardcore study the phenomenon that happens on the surface of the sun. Now, we've been looking at solar flares and sunspots and everything like that for a long time now, but it's only been very recently that we've been able to get to the bottom of some of those phenomena and start to understand what it actually happens. And in today's episode, we'll start to talk a little bit about why that's important to us here on the planet, even though we're so far away from the sun. Now, the other reason why this, I think, is a little bit important is because it's summer. We're just now getting into the beginning of the summer here in the Northern Hemisphere, where most of our audience is. And so I thought we'd just kind of piggyback on the back of the fact that you guys are staring at that flaming ball of gas in the sky every single day and just take a little bit of your brain space by talking a little more about it, making sure that you understand more about it. And so before we get into talking about the science of the sun, I think it's important to everybody out there, scientists, laymen, everybody out there, to really understand some things that I just think are fascinating and kind of some ground rules that we need to cover up front.
Definitely.
I think it's important to everybody that you really understand that this is a lot more than just a light bulb. I mean, the sun is awesome. And when I say awesome, I'm using the literal version of that word. This thing is awe-inspiring, and
definitely,
it is huge.
Yeah. About 1 million Earths could fit inside the sun.
1 million Earths. And even though it is made almost entirely out of gas, there's actually over 330,000 times the mass of our rocky planet inside the sun.
Yep.
Those kinds of numbers I can't even fathom. I can't even really wrap my brain around
thinking of a giant little scale. Sun on one side, 333,000 Earths on the other.
300. That's ridiculous. Now, the only reason that it looks so relatively, small in the sky around us is because it's so far away. How far away is it, you say? Well, I actually happen to know this one off the top of my head because I'm interested in things like the speed of light travel. But it takes 8.3 minutes. 8.3 minutes for light to travel to the Earth from the surface of the sun. Now, just to put that in perspective, 8.3 minutes is long enough for most of us to make and eat a full sandwich. I mean, that's how long it takes for light traveling at these phenomenal, unrealistic, unfathomable speeds to get from the surface of the planet to us out here in the boonies. Yep. And yet, despite that phenomenal distance, it can still reach over 100 degrees on the surface of this planet from that ball of gas.
Yep. All from that ball of gas, which really is a star.
It is a star. And
you have to stop and think about that.
How does our star stack up against the rest of the stars in the universe? Do we really know? Do we have enough of a sampling that we can tell is our star
it's
awesome?
Kind of a middle-of-the-road star, kind of your average star.
Oh, that's kind of underwhelming.
Well, and on top of that, it is designated as a yellow dwarf.
Ah, dwarf.
Yeah.
Although
it's not really big.
The dwarves in like Lord of the Rings were some of my favorite characters, so I guess it could be worse. Could be a yellow hobbit.
You mentioned that the sun is 333,000 Earths. Yeah. The other thing to note is that if you take the entire mass of the solar system, everything, all the planets, with the sun, that the sun compromises 99.86% of the entire mass of the solar system.
That's including like the asteroid belts and even Jupiter, which we know is phenomenally large.
Yep.
That the sun is still 90. Wow. I mean, I think it really nails the point home, you guys. The sun is awesome. I mean that. It's huge. It's phenomenal. It is just this incredible thing. And taking it for granted is a very dangerous thing. And I mean that because it is it is a flaming ball of death in the sky hanging out there above us. I mean, the gravitational forces, which is basically what has caused the sun to ignite, are so great that this ignition has been caused in nothing but gas. I mean, the sun is comprised, correct me if I get these numbers wrong, but it's like half hydrogen, half helium. Is it roughly around there?
3/4 mass is hydrogen. The rest of it's helium. About 2% is heavier elements.
Right. So less than 2% of that is other heavy elements. It's mostly just burning. And actually, I know you were going to correct me on this because I keep saying the term burning, and it is not on fire. Because as you might have learned in our last week's episode when we were talking about the science of barbecue, fire requires oxygen. And so the sun is not on fire. There's no oxygen up there. All of that energy, all of that massive amount of heat and light that we witness here more than 8 light minutes away from
nuclear fusion
is nuclear fusion. That's right. Like, comparing it to the bomb that was dropped on Hiroshima is nothing. It's not even worth talking about. This is gravitational forces reacting so strongly with all of this gas right next to each other that it has actually caused it to actually for hydrogen to slam into one another and become helium. And other heavier elements. As you said, there's like 2% other heavier elements. But that the gravity is so much that it's just pushing these things together until they can't be separate things anymore. They have to become something new. That is just phenomenal. It's something that we don't really witness in our everyday lives or even on the surface of the Earth simply because the gravitational forces and everything are just on a completely different scale. And thank God we don't witness that on an everyday basis. But it also goes beyond that. I mean, I mentioned real quickly that the sun is not to be taken for granted.
No.
I figure before we start talking about all the other science in regards to this, we should talk a little bit about ultraviolet rays.
Yes.
Because these are a very real part of our everyday existence here on this planet. And despite having an atmosphere to protect us, it's not always 100%.
No. UV radiation, you know that it can cause sunburn on your skin, but also it can cause sunburn-like lesions on the back of your eye, on your retina, in less than 90 seconds.
So if you stare at the sun for less than 90 seconds, it can result in more or less a sunburn on the inside of your eye.
And it's also been linked to cataracts, the yellowing of the lens on your eye. There's some evidence that there is a linkage there.
Now, you actually have a note in the doc here that looking at the sun delivers about 4 milliwatts directly to the retina and can, like you said, a sunburn type lesion, but also if you keep staring, can cause permanent damage that you can never recover from.
Yeah.
You'll just be blind by staring. And that, remember, is on these phenomenal astronomical scales that this thing is millions of miles away and can still blind you. This is not... We're not joking around.
This thing is not to be trifled with.
Exactly. And it's not. It doesn't stop at your eyes either. You mentioned real quick about sun tanning and sunburning. Give us some of the science behind that.
Look, a sunburn is your body's reaction to DNA damage.
Whoa.
The UVs are actually what they're doing is they come in and they hit your DNA. And then you may know you have little ladders that connect your DNA.
Right. It kind of looks like a big twisty ladder.
Yeah, twisty ladder. We're both laddering. When the sun hits your DNA, it sort of makes those ladders break apart and connect, like one side connect together, which makes the DNA bulge on one side, and that's not properly functioning.
That doesn't sound healthy at all.
No, it's
now,
a cause of cancer.
Actually it causes cancer?
Yes.
I mean, it's been pretty universally proven that ultraviolet exposure can cause skin lesions, which can lead to skin cancer. And
yes.
You had a note in our doc somewhere in here. I don't have it handy, but it's like 90% of all skin cancer is linked to sun exposure.
90% of non-melanoma skin cancer, which affects 1 out of every 5 Americans, and 65% of melanoma cases, it's all from UV DNA damage caused from the sun.
Wow. So again, not to be trifled with. In fact, I would like to actually sidetrack. We have more information in our show notes about skin sunblock and sunscreen. And I didn't want to go too much into it in this episode because we're talking about the sun, but I do want to mention kind of offhandedly, the FDA here in the States has recently started to more normalizing an overview of sunscreen and sunblock. So some of the terminology is going to start changing soon. Some of the packaging labels are going to start changing soon. And I think it's important for anybody that gets a large amount of sun exposure on a daily basis to know at least a little bit about this so that you know more about the type of protection that you should be using. And you should be using protection at all times. I mean, the sun is not to be trifled with.
No.
And when I say that it's not to be trifled with, I don't want to just be talking about ultraviolet rays, which is one of the major things that we see here on the planet. But there are other things that have a very real impact on life here on Earth that you might be taking for granted. You probably all have heard the term solar flares. Now, I will admit, Heather, that before starting to do some research for this show, I was a bit of a layman on this subject, and I never really understood, and to be honest, I still don't understand, but there are several different categories of emissions from the sun, and solar flares is just one category. I had taken it to indicate that things like coronal mass ejections and solar prominence and all of these were just flares, but they're actually different things. So if you don't mind, maybe we can go like one by one and categorically kind of explain what each of these are.
Sure.
Might work for you? So let's start with solar flares. Tell us a little bit about what a solar flare is.
Solar flare is when magnetic energy, because the sun isn't just sitting there. It's got a lot of boiling and rolling. There's a lot of hot plasmas rolling around, and it'll cause...
And it's got a very strong magnetic field.
Oh, yes.
A very volatile magnetic field as well. When we get to talking about a little bit more in some of these other solar phenomena, we'll explain that a little more in detail.
Yep. So it causes these magnetic fields. And when you have, in certain locations, you can have magnetic energy build up in the atmosphere. And when that magnetic energy is released, that's a solar flare.
And this is what you see primarily pictures of, right? When you see like big waves of look like fire being ejected from the surface of the planet, kind of curling over.
It's more of just radiation is emitted across the entire electromagnetic spectrum. It's released about equivalent of 100 megaton hydrogen bomb, all exploding at the same time.
Yeah. Yeah, we're not screwing around here.
No.
Now, okay, so if those big arcy things aren't solar flares, is that a prominence? Is that what?
Yes, those are more prominences, large, bright features extending outward from the sun. So you have they're very often in a loop shape.
And that again is caused by the magnetic field. Kind of, it extends from the surface and then it gets caught in the magnetic field and kind of dips back towards.
The magnetic field it'll it's like a loop, and the loop will sort of extend out from the surface of the sun, and then the plasmas and hot gases and things can ride along that loop.
It's also seen, if you recall, from the from Spider-Man 2, Dr. Octopus's experiment with the big... Okay, I won't go there. It's completely scientifically inaccurate, but kind of cool looking. But okay, so
cool.
we've talked a little bit about flares, and we've talked a little about prominences. Now, I've heard also the term coronal mass ejections and solar energetic particles. Am I getting that right?
Yes, you are.
Okay.
Now,
what about the mass ejections?
Now, sometimes you have a prominence, it's this big loop of stuff. There's occasionally it can break off.
Oh.
And if it breaks off, then it is a coronal mass ejection. It's literally a mass of the sun, a little chunk of the sun, breaks off and goes hurtling through space.
And that just kind of gets carried along the solar winds and runs
solar
into
winds,
planets or whatever else is in the way?
Yeah, with other isotope plasmas along the magnetic fields.
No, I'm curious, and maybe you don't have an answer for this one, but wouldn't it take an incredible amount of force and energy to escape the sun's gravitational pull? I mean,
yes.
Is that actually something that, is it a pressure from the surface of the sun, or is it carried along by magnetic fields, or what? Is it a little bit of both, or how exactly do those eject?
But I believe a lot of it is literally... just these plasmas riding along these magnetic lines out from the sun, and then it kind of is able to shoot it off enough that once it breaks off, it has... Now, sometimes it can fall back onto the sun, but occasionally it'll have enough velocity to just shoot off from the sun into space towards possibly planets or...
So it's just a matter of escape velocity at that point.
Yes.
What makes the difference between a solar prominence and a mass ejection. Now,
to some degree, yes.
That is pretty unfathomable to think of when you remember that I had just said that it's the gravitational forces of the sun that are causing it to glow, causing hydrogen to become helium. So it's so strong that it can force atoms together, and yet it can also force things away from it with such power that it can actually escape its gravitational pull. Yeah. That's pretty darn fascinating. Now, what about the solar energetic particles? Is that something different than a mass ejection?
Sort of. They're just, the mass is more atoms and plasma. Solar energetic particles are just high energy particles leaving the sun. They're protons, electrons, heavy ions.
Oh, okay.
This is what puts a lot of danger for astronauts in space and like people on the space station.
You know, that's probably a good point, kind of sidebar here, is the fact that that's one of the main reasons that modern science has been studying the sun so closely, is because as we spend more time in space, as we send more people to either live or travel or study things in space, they are not protected by any sort of atmosphere of any kind, and except, you know, maybe if there happen to be if the Earth happens to be between them and the sun. But that
one other
doesn't
thing to note that it's almost not so much the Earth's atmosphere, it's the Earth's magnetic sphere. It's our magnet. And the space station is farther out, so it has less protection. Like if you're at a higher elevation, you can get a sunburn faster because there's less atmosphere to protect you. Now, and if you go onto the moon or Mars, obviously you're outside of the Earth's magnetic field.
Now, it can even happen sometimes that some of these ejections and flares and prominences and all this stuff shooting off from the sun, is this something that astronauts have to actively shield themselves from? Like if they know that a solar something is coming, do they have to duck and cover or what?
Yeah, if they have enough of a warning, which is where we were just recently being able to have, you know, more and more of a warning of when these things are happening, then they can go to a more shielded area if they're able to, or at least not if they're on a spacewalk, at least come back into the station.
Yeah, but anything's an improvement from being out in naked space.
Yes.
But these things also affect life here on the surface of the planet in ways that are incredible. Let's talk a little bit about geomagnetic storms and auroras, which are kind of a side effect of the same thing. I mean, if you've got a geomagnetic storm, you've got auroras. But
they're just a visual effect.
Right, and most people out there are probably familiar with the Aurora Borealis, which is usually only seen in like polar regions. And it's basically...
South Pole to Aurora Australis.
Right, and so those are, correct me if I'm wrong, but those are basically plasma being refracted through our outer... Is it the outer magnetosphere or outer atmosphere?
It's the magnetosphere.
And in such a way that it kind of is visible.
Yeah. What it is it's the solar wind and has hot plasmas, free electrons, and it's emitted by the sun in all directions. And, you know, just for, you know, it doesn't have to necessarily be a coronal mass ejection to get aurora. That gets a lot more. But, you know, we'll have light auroras occasionally from just the regular solar winds. And they're they usually reach the Earth at about 250 miles a second.
So really slow. Really slow.
Just slow. And during a magnetic storm can be even several times faster.
Now, some of those coronal mass ejections and prominences, if they do shoot off, so not prominences, because those don't shoot off. I'm understanding now. I'm getting this.
Okay, you're getting it.
Terminology is entering my brain. So let's talk about the mass ejections and the solar energy particles. Those energetic particles can also cause auroras too, right?
Yes.
Okay, so I've got that.
You've got it.
But they can do a lot more than just auroras. Now, first of all, I want to circle back on something. The coronal mass ejections, how frequently do they occur?
One thing to note about coronal mass ejections is that the sun has a sort of a cycle. It has a quiet time and a busy time where it's more active, about an 11-year cycle.
Oh, really? That's a cycle in the magnetic forces, basically?
Yeah, that is correct. And you can even see it like where sunspots occur in different places depending on where the cycle you are.
Oh, and you said, okay, so that's every 11 years.
Every 11 years it cycles so that it's very busy. Okay. When it's near the solar maximum, when it's really active, you can see 2 or 3 coronal mass ejections a day.
Oh, wow. Wow, that sucker is shooting a lot of stuff into space.
Yeah, and at a minimum, it's only about once a week.
But even at a minimum, once a week. Some of these, do you know, we're going to start talking a little bit about geomagnetic storms, and there have been a few recorded occurrences of some major geomagnetic storms which have been caused by ejections from the sun of matter and energy from the sun at basically spike rates. Did all of these occur during solar maximum, do you know? Or is this something that can basically happen anytime when the sun decides to just go nuts?
It's definitely much more likely to happen during a solar maximum. But, I mean, as far as we know, it could probably happen anytime. And you always have to kind of watch it. It's just when there are so many more and it's very active and it's much more turbulent.
You're just playing the odds at that point.
You're just playing the odds, and it's much more likely that you'll have a large one.
Right. Now, I want to touch on some of these briefly, but I think that geomagnetic storms are actually so fascinating and kind of big, kind of a big sciencey subject. We could probably dedicate an entire episode to that.
Oh, yeah.
We might.
Maybe.
Because I find this interesting, but I don't want to dwell on that particular topic too much. But let's talk about the power outage in Quebec real quick that happened. Do you have the date handy of when that occurred?
The Quebec outage happened March 13th, 1989.
That was actually, I remember this. I remember when this occurred. And it actually wasn't, it didn't only affect Quebec. A lot of the northeastern United States was affected as well.
Yep.
Now, why was it particularly that region that was hit so hard by this solar energy coming in?
Some of it was its northern latitude, so obviously it has a lot more to the Aurora as it's coming in more. But the utilities that had the most damage or the most interruption in service had very long transmission lines. So they were able to build up a lot more of this magnetic interference. And also,
now, is that basically because the energy coming in hits more of the surface area of their transmission line? Is that
it's not right? If it's broken up more, then you build up. You build up a little bit in each little section.
Okay.
And it's a very long one, then you can build up in that entire section, and it all adds up to a much larger number. Also, that Quebec sits on a very large rock shield, which prevents the current from sort of grounding out.
Oh.
So it was building up, and it had these long lines that was building up even more, which meant it kind of overkilled the system.
And that was just by random electromagnetic energy entering our atmosphere and being absorbed by the power grid.
Yeah.
So much, to such an extent that it shorted it out. It overloaded it.
Yeah, it couldn't handle what the sun was just sort of spilling out accidentally.
That's amazing, but apparently these things have been happening for the entire life of the planet. I couldn't even fathom what ancient people would be thinking of this if it had some effect on their normal life. Like, you had told me a story about some previous geomagnetic storm that had caused auroras, which are usually only seen in the far polar regions, to actually be visible at the equator. Sailors on the equator noted seeing an aurora.
Halfway up the horizon, halfway up the sky. The captains noted in their log that they could see, crimson lights in the sky. Cubans could see the aurora directly overhead.
And there was one in the 1850s or something like that, where it's a funny story. Why don't you go ahead and tell it about the California?
It was actually Colorado in the Rocky Mountains.
Oh, my bad.
That's okay. But it was really bright, so bright that gold miners in the Rocky Mountains woke up, ate breakfast at 1 a.m.
At 1 in the morning.
That the sun had already risen, and it was just a cloudy day.
Just because there was so much aurora activity above the clouds.
Yeah, you could read your newspaper by it.
That is bound to happen again sometime within our lifetimes. I mean, this is just something that happens. The sun goes nuts on occasion. And, while we're talking about the sun going nuts, I want to talk even more about, we've kind of glanced over sunspots, which is something that I think a lot of people out there have heard of, they've seen pictures of. But I'll be honest, we talked about this in my astronomy class in high school. We'd spent months probably weeks, but it felt like months because I was in high school, trying to understand sunspots. And I still cannot wrap my brain around it. I know it has something to do with magnets.
Yes.
How do they work? I mean,
how do they work?
Can you try to explain to me, or maybe not me because I might be too dumb to understand, but what is a sunspot and how does it happen?
It's caused by intense magnetic activity. So intense that it inhibits the convection of materials. So it sort of just stops all the plasmas and stuff in a certain section of the sun from rotating and doing anything with its neighbors.
Wow. Now, convection, we haven't talked about on this show, but it's a basic chemical thing where hot things rise and cold things fall.
Yeah.
So, but you're saying that because of the magnetic forces, the cold stuff doesn't fall away from the surface?
Yeah, it's got a little pool of stuff that's not allowed to really rotate with or interact with anything else.
Wow.
And so that area cools.
Oh, and that's why it appears dimmer than the rest of the sun.
Yeah, because it doesn't have the ability to glow as much.
Now, but we're talking about, like, everybody's probably seen pictures of sunspots. They look black.
Yeah.
But you got to keep in mind that in order to take a picture of the sun, you have to use filters.
Yes.
I mean, you can't just look at it with the bare naked eye. First of all, that's bad for you. But secondly, it would be a terrible picture. And any photographer knows that. So you were telling me, and I didn't know this. I should have realized this. I mean, this is kind of a common sense thing. But the reason that they look so dark is because of the filters that have to be used to take a picture of the surface of the sun. Yeah. It's only in comparison to the rest of the sun that they look so dark.
Dark. It would be brighter than an electric arc.
Oh, brighter than an electric arc. But it only looks dim because you're talking about comparing it to a nuclear explosion.
Yes, I mean, it's so much brighter that it looks dim in comparison.
Black in most pictures.
Black, yes.
I think that's one of the reasons that I didn't understand this in astronomy. They never told me about the relative brightness thing. Or maybe they did and I was asleep. I don't know. I did really well in science in high school. I promise. But another awesome thing. Okay, this is the last awesome solar phenomenon that we're going to talk about in today's episode. But we've saved the best for last. I'm just going to say its name because you will love this.
Go ahead.
Solar tsunamis. They do exist.
Yes. They are real.
Now, one of the guys in our chat room said that if we use that term too liberally in today's episode, all of our viewers would be going to work tomorrow wearing tinfoil suits. So I don't want to scare you too much. It's not that much worse than your average solar flare. Am I right? Or is it?
No, it's a solar tsunami is really a surface event. It was just discovered in 1997 by the Solar Heliospheric Observatory. Actually, when they first saw it, solar physicists kind of wondered what they were looking at. They're like, no, that can't be real. That can't be what we think it is. Now, There's just no way.
I think the term tsunami is a little of a misnomer for this anyway, because I mean, here on the planet, on Earth, that's where we live. Unless you're watching this somewhere else, in which case, hi. But here on Earth, tsunamis are caused by earthquakes.
Yes.
The sun has no Earth. So it's kind of a misnomer.
Sun has no... Yeah, Earth to earthquake.
Right. So what exactly causes a solar tsunami? Do we know?
Well, that's kind of what we're trying to figure out. We've just discovered them and we've just sort of been able to catch a few of them. And so we're really analyzing the data that we have to figure out where they start, how they are. I mean, really, it's just sort of a wave on the sun. I mean, it does raise higher than the diameter of the Earth.
The scale, it just gets to me.
Yeah.
We're talking about an event on the surface of the sun that's larger than the planet. Yeah. No big deal.
It's okay. Not a big deal.
You said it's a surface event, but some of the videos that we have do show ejections. Is this just like basic? Yeah. But it's no more, or it's no massive thing that's any worse than your average coronal mass ejection. Am I right?
Yeah, it's not any worse, I don't believe.
Okay.
We've only been able to see a few. So it's just sort of, we're able to see, this sort of wave on the surface of the sun, and then some stuff gets, splashed up into the sky.
The heliosphere?
The heliosphere.
Can I use my big words now?
Use your big words.
Okay. Now, you've said we're seeing these things. I think that's a good point to kind of transition into, the introduction of SciByte is we're looking at the tools and technology that science is using to uncover these things. So let's go ahead and do that. Now, I will admit I don't have a whole lot of notes on this subject. I'm going to be relying on you, Heather, to tell everybody all the details about this. So let's get started, though, with one that we've covered on a previous Jupiter at Night episode. This is called stereo.
Yes.
Now, some of you out there that might not be, if you didn't watch Jupiter at Night, or if you haven't been, really into this, you might have already seen some of the footage gained by the stereo probe, because they actually premiered it during the Super Bowl this last year. NASA was very proud of this.
Yes.
Tell us a little bit about what stereo is.
Sure. The Solar Terrestrial Relations Observatory.
Fancy.
Stereo, because we're literally looking at it in stereo. We shot off two practically identical satellites, one going ahead of the Earth's orbit and one going behind. Okay. And they'll separate enough so that at a certain point we can see opposite sides of the sun. So we can not only look at a solar flare or a coronal mass ejection from one side. I mean, you can see a picture of something. But if you get that second image in, it gives you that 3D imaging. So it kind of gives you a much better view of how they are, what they are created, where they start off and what they're actually doing.
Yeah, and there's some fascinating imagery that's come out of this, and I'm probably showing you some of the pictures now. Now, the stereo mission right now, and actually just earlier this year, I think it was in like January or February of this year, of 2011, was when we finally reached that perfect 360-degree view. But it won't stay like that.
No.
I mean, these are going to start drifting even further, right?
Yeah. Well, essentially, if you picture the solar system like you're looking down on it, you see the sun and the Earth.
I picture that a lot. That's my
usual.
Picture
that a lot.
Yeah.
Of course.
Looking down on everything.
So we have one going, clockwise and one going counterclockwise along the orbit of the Earth. They'll get to the opposite sides, and then they'll continue going around. They'll meet at the back side, on the opposite side, and then they'll curve back the other way. So it'll only last so long that we'll be able to see a 3D image of the sun.
During that time, I mean, that might be several years.
Yeah, it's going to be a few years that we'll be able to get a lot of data off of how these things work.
I think that's great. I think that not only taking pretty pictures is important, but some of the information, there are other studies attached to the stereo probes, right?
Yes.
What are some of those other things that they're looking at?
Well, there are 4 main instrument packages that are sort of looking at the sun. One is the Sun-Earth Connection Coronal and Heliospheric Investigation.
They give these things the best names, I swear.
It's because they want awesome acronyms. CCHI.
CCHI, okay.
So this is looking at the study of the 3D evolution of coronal mass ejections from their birth of the sun's surface, through the corona, through interplanetary media. It's taking remote images of these coronal mass ejections as they erupt and travel through space. And
this is one of those early warning systems that we were talking about earlier. That using this system, we'll be able to detect the formation of a coronal mass ejection before it actually occurs, theoretically. So that would allow...
The more we know how they evolve and how they weave and travel through the interplanetary media, the more we'll be able to sort of see, this one's just starting. I think it might be a problem. Oh, this one's starting, but yeah, we know from past data that it's not something we really need to worry about. Just kind of keep it on the back burner.
Now, now what about SWAVES? I love these names. I don't know what SWAVES stands for.
Waves.
S-waves.
Stereo waves.
Oh, stereo waves. Okay. What's this one studying?
It's a radio burst tracker. It detects the ahead of these coronal mass ejections. You have sort of a shock wave of radio waves.
Oh, how does that happen? Is it just because of the mass is aggravating things as it comes towards us?
Yeah, it's part of the electromagnetic spectrum. So it's it's part of the light. So it's just sort of pushed ahead of the rest of the particles.
All right.
But because it's traveling at the speed of light, that's practically the first thing we're going to be able to see.
Probably. Yeah, because as you mentioned earlier, these coronal mass ejections are slowpokes, only like 250 meters a second.
Oh, yeah.
Yeah, I mean, that's nothing. Okay, so these are the ones that are actually tracking things that travel at the speed of light. Well, that's awesome. Now, is there any specific reason other than early warning that they're looking at these, or is that the primary?
Yeah, you can also detect and measure density of the interplanetary magnetic fields. We talked about everything travels along magnetic fields. For Aurora with the sun and the sunspots. Well, there's sort of interplanetary magnetic fields throughout the system. And if we know more about them, then we can kind of see how it's like it's flowing down an eddy or something.
Right.
We'll be able to see how it's made up and where it's likely to go. So we see there's a battle shock. Here's how it travels through the interplanetary media. Now we'll have a better idea of how they start, where they'll go, how they'll travel to get there.
Yeah. Okay, now one more to study here. Oh, there's 2 more. Jeez, there's so much science going on the sun, people.
So much science.
Tell me about impact. I think that's the best word, though. I think that's the best. Let me say this one. Because I don't understand what it means, I'm going to ask you to explain it. In situ measurements of particles and CME transients. What is in situ?
In situ. It means getting stuff while you're there. This is the kind of thing where if you go to Mars, you make your fuel to get back while you're on Mars.
I see. Okay. And so that's impact. What are they actually checking out here with CME transients?
Coronal mass ejections.
Yeah.
There it's measuring the electrons and the embedded magnetic fields of particles in the solar wind. So it's actually taking these solar energetic particles that we spoke about earlier and characterize them. So we can say, this is how they're traveling. This is what they're doing. So we look at the actual particles themselves. So
based on some intense analysis of each of these individual coronal mass ejections and solar energetic particles, we can start to categorize them in different ways so that we can determine, again, this is great for early warning systems. You can determine which ones are going to be a primary threat to things like power grids or astronauts in space and which are nothing to worry about just by taking an intense study of them.
Yes.
Okay. One more. Plastic.
The plasma and suprathermal ion composition.
All right. Well, I like heavy ions. Tell me about what these guys are checking out.
This is measuring the density, the speed, the flow, and the material of the solar wind. Just, regular solar wind, what it's doing.
When you say solar wind, we're talking about the actual, the ions, the stuff that's carried by these magnetic waves, right?
Now, the solar wind is always being sort of puffed away from the sun. It's, particles and heavy ions just being spread from the sun at all times.
I actually think that you mentioned this earlier, and I kind of just ignored it when you said it, but you said that stuff is leaving the surface of the sun all the time, and these other things like flares and ejections and energized particles are basically like condensations of that and more heavily populated regions of that solar wind. But I think that is important to restate is that the sun is putting off energy all the time in every direction. Yes. Otherwise, we wouldn't get hot heat and light here on the surface of the planet.
Yeah.
I mean, that's what it is. They're pushing off ions and photons and junk and heating stuff up. So, yeah, okay, sorry. I didn't mean to sidetrack too much. So about the solar winds, this is what plastic is checking out?
Yeah, it's characterizing the protons, the alpha particles, the heavy ions. It's giving us diagnostic measurements of the form, the mass, the charge state, the composition of these things, and of coronal mass of the solar wind and coronal mass ejection plasma.
This sounds like a pretty comprehensive package. All of these instruments are being carried on the stereo probes?
Yes, it's these 4 instrument packages on the stereo. So you're looking at, tiny particles, you're looking at the wavefronts, how they move, how they form. So it's just sort of it gives you it's 4 packages that can give you a really good overall view of how these things act and to give us the most bang for our buck out of these.
And this is an ongoing mission. I mean, the stereo mission is going to continue for several years, even after they go behind the sun and they won't be getting pretty pictures. All of these other instrument packages will, in theory, continue functioning, right?
Yes. I mean, they'll still continue functioning. Essentially, if you think about it, they may be on the other side of the sun, but they're still the same distance from the sun, really. Right. It's just the distance from Earth that's affected. So they'll still be transmitting data, and we'll get the data as often as we can for as long as we can.
And actually, since you mentioned transmitting the data, this is the one that's got some pretty serious tech specs on it, right?
I think so.
They're able to transmit, if I remember right, at like 720 kilobits a second, which is, okay, we probably got better internet speeds than that here at home, some places in the world, but we're talking about space, people. This is high range, high speed internet right here.
Yeah.
And I thought it was interesting.
Long distance wireless.
Yeah. I thought it was interesting to note that the power consumption on this stereo says is only listed as 475 watts.
Yeah.
I've got a bigger power supply than that in my PC rig at home. I think I draw more power than that on a regular basis.
Well, that's the thing. Power is easy to get on Earth, so they don't have to build things to be, they can be power hogs. But for satellites, you're only going to get so much power. The more power you have, the more it heats the inside of the satellite. Then you have to worry about overheating your instruments. So everything is about, the least amount of power, the most amount of data, how to get it back to us.
Efficiency and wear and tear over time, because you want these things to last as long as they can. And you can't just send somebody out there to repair it.
No, it's not something you can call AAA for.
Now, speaking of calling AAA, though, no, there's no relation here. But, we've got so much information in our show notes. I mean, oh my goodness, there's information in our show notes.
Yes.
Clearly, Mars, you are interested in the sun because you found some. These are probably all from your personal bookmarks. Not only do we have tons and tons of web pages here that you can check out for more information about the sun itself and heliophysics at NASA and the stereo system and tons of wiki pages on all the topics that we've talked about today. But there's also, as always, social media.
Yep.
And so there's a Twitter for space weather. There's a Twitter for the sun today. The Solar Dynamics Observatory, which is one of the leading study centers on solar activity, has both a Facebook page and a YouTube page where they regularly put up videos. And, well, if you're watching this, you probably love videos. So you might as well check that out as well. And you know who else has some social media out there that you guys can check out is us.
Yeah.
That's right. You can see most of the stuff that we post over at facebook.com/Jupiter Broadcasting. But you can also follow both of us on Twitter, but not on Facebook. And not yet on Google+, but that may be coming soon. But if you want to check us out on Twitter, you can follow me. I am at JB Jeremy.
And I am at JB_Marsbase.
That's right. And I got to say, just like I said in last week's episode, if you're more interested in the sciencey stuff, she's the one to follow. I do a lot of video games and stuff, which are fun. They're awesome, right? But it's not exactly science. And in addition to that, if you have any commentary on future topics for the show or anything of that nature, I would totally encourage you guys to head over to jupitercolony.com. We have a really active little community of science geeks over there just getting their nerd on about different topics. There's a few on there that we will probably use for future episodes, others that are just fun to talk about. And in addition to all that, why don't you lay our email address on us? Look, I remembered it this time.
I know, I was about to interject. Email us at SciByte@jupiterbroadcasting.com.
And that about wraps us up for this week's episode of SciByte. But I need to tell you guys, you're going to want to watch next week's episode because if you're watching science, I know you're going to be interested in what we're talking about next week, which is...
the Large Hadron Collider.
The one and only.
One and only. Has it destroyed the Earth? Not yet. But we will be talking about what it does, what they're studying, how it works, looking more about the gritty details about what's going on there.
And just why exactly you need a gigantic circle to do science. All on next week's episode. So, speaking of gigantic circles, I hope you have enjoyed this episode all about the sun. And until next week's episode of SciByte, stay cool, everybody. That's terrible. I'm sorry I used that as our sign-off. All right, we'll see you next week.
That was awesome.